So we're going to look at the visualizations of these distributions and how you're able to tell from just the distribution how a distribution that is skewed to the left and skewed to the right looks like. Now, you must understand that it's important that you understand these pictograms, which will give you a picture of how the distributions look like. So topic 1 specifically helps you understand presentation of data. So we're going to look at skewness and kurtosis briefly. So what does skewness really talk about? Skewness simply looks at the measure of asymmetry that a distribution may have. Asymmetry is simply the shape of your distribution, whether it is looking like this or whether it is looking like this or whether it is looking like this. So when you have an asymmetrical distribution, it means the left side mirrors the right side. If the distribution is bending to the left, we say this is skewed to the left. Or others will say it is negatively skewed. The distribution looks like that, it means it is skewed where? To the right. Similarly, you're able to tell from a box whisker plot where you have 3 scenarios. Number 1 is a normal distribution. It is 50-50. Number 2, it is skewed to the left because the gap here is bigger. Number 3, it is skewed to the right because the gap here is bigger. Then if you have a distribution which has 50-50 left and right, these ones are distributions. So this is called a box whisker plot. It's called box whisker plot. A box whisker plot is there to show you whether you have outliers in a distribution. It is important that you also learn how to draw a box whisker plot to scale. When you're illustrating, you could also use a number line down there. So if you have a figure like the smallest value of x maybe is 9, the highest value of x maybe is 50. Then you have q1, maybe this is 19. You have q3, this is 29. So how do we draw this box whisker plot? It is important that you illustrate with your number line. That's important. All right, maybe 5, 10, 50, or maybe this is -10, 0, 10, 20, 30, 40, 50. Then you draw your number line. So the minimum value is at 9, you put your 9 there. Maximum value is at 50, to 50 there. You draw your lines there. Okay, then the lower quartile is at 19. Put 19 there, and the upper quartile is 29, 29 there. And for instance, if your second quartile, which is the median, is 25. Second quartile is 25. So 25 is somewhere there. So this is what? 9, this is 19, this is 25, this is 29, this is 50. So you're able to tell the distance from here to here is a 6. The distance from here to here is a 4. So you can tell that this is skewed to the left. Now, the interquartile range is the difference between the lower and the upper quartile. So 29 minus 19, we get 10. So this is called the interquartile range, which is 10. Then you multiply the interquartile range times 1.5. It's a standard figure. 1.5. All right, 1.5. So 1.5 is a standard figure. So 1.5, when you multiply to the 10, you get 15. So 15, you add it to the 25, the 29, sorry, and 15 you subtract it from the 19. So when you add 15 here to the 29, what do we get? 15 plus 29, we get 44. So 44 is somewhere inside here. So meaning this is called our upper limit. Then from the 19, you subtract what? 19 minus 15, what do we get? We get 19 minus 15, we get a what? A 4. So 4 is somewhere there. This is called our lower limit. So we can tell from here that our only outlier is 50 from the distribution. So I think I taught all this during the day. I'm just trying to emphasize things that you thought you knew, but you did not know. So theoretically, an examiner will just ask you, describe the 5-number summary for a box whisker plot. Now, the 5-number summary for a box whisker plot consists of, number 1, the smallest value, which is x mean. The smallest value. So it has the smallest value. All right, then secondly, what do we have? We have the following: the smallest value, then the first quartile, the second quartile, the third quartile, and the largest value of x. So you get your 5-point summary for a box whisker plot. So it has x mean, we have x1, x2, x2 is also called the median, x3, which is the upper quartile, and x max. Right together, these are the values that give us our 5-point summary for a box whisker plot. All right, so let's construct a box whisker plot from the following data here. We are given data 20, 22 up to 92. So how many do we have here? We have 11 data sets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So a 5-point for 11-day period. Number 1, we find the lower quartile. The lower quartile is a quarter of n. So a quarter of 11 is 2.75. We round up, which is 3. The lower quartile is 3/4 of 11, which is 8.25. We round up, which is 9. These are positions, the 9th and the 3rd position. So you count 1, 2, 3. This is our Q1. 4, 5, 6, 7, 8, 9. This is our what? Our Q3. This one is the minimum value of X. This one is the maximum value of X. Please, if there's a question that I do not want you to ever fail, it is such a one. You should not fail such a question because everything is explained. If I'm a little bit fast, please, you could ask. At this point, any questions? Was that a hand?
Yes, Collins, I've got a question.
Hmm?
I noticed a difference in the skewness between the box whisker and the bell-shaped diagrams.
Okay, I'll come to
Because
that as I'll discuss.
oh,
Yeah,
all right,
just want
okay,
to ask
thank you.
questions in what we've done so far. All right, so if this is clear, I've already explained the interquartile range is simply the difference between the highest and the smallest value. So 70 minus 29, which is 41. You multiply a 1.5 to this one here to give you the correction term. So here we're going to have the number line like I showed you. It's important to illustrate this. We have 92, we have 20. And in this case here, we want to see. Okay, so can you hear me? Network cut me out. So I just want to explain a few things here on what we have done so far. So we identified the lower quartile, which is our Q1 here, the upper quartile, which is 70 Q2. The difference between 70 and the lower quartile gives us our interquartile range. Yes, Maggie, that's a hand.
Yes, I know the similarity between this one, the last part and the previous part on the box and whisk approach. On this part, on the second part, I can easily understand, but on the box and whisk approach, the way you were doing the calculations, I think I was just seeing numbers and I think I'm failing to connect.
I'll explain that, like I said. You would only ask questions from as far as I've just explained. I just gave an overview of what I'm going to explain. So if there are any questions on what I've explained that anyone has been left behind, you could please ask. If everything is okay so far, that is fine. So I'm saying in this instance here, the lowest value of X is what? 20. That's a 20 there. The highest value of X is what? 92. That's a 92 there. The lower quartile is the third figure, which is 29. And the upper quartile is the ninth figure, which is what? 70. When you subtract 70 minus, you get our interquartile range. So interquartile range would be 41. Then you multiply the 41 times 1.5. What do you get? 41 times 1.5. What do we get?
61.5.
61.5. So this 61.5, you add it here.
Hello, Collins.
Uh-huh.
I just want to find out where is the 41 coming from?
The 41 is the difference between the upper and the lower. It's called the interquartile range. So you subtract the Q3 minus Q1. So 70 minus 29, you get 41. That's a 41. Then you multiply this 41 times 1.5, you get the correction term. So to find the lower limit, you multiply 1.5 the interquartile range, which is 61.5. So 61.5, we will subtract it from the 29 here. So 29 minus 61.5, we get negative 32.5. So negative 32.5 is somewhere there. That is called our lower limit. The upper limit, we add the 61.5 to the 70. We're going to get 131.5, which is somewhere there. 131.5. So in this case, we discover that all the figures are swallowed inside here. So between negative 32.5 and 131.5, there are no values, if we're going to check here, that are outside range. So this entails us that there's no what? Outlier. So distribution tells us that there's no outlier. And also to come up with a 5 number summary, we have 20, which is our lower. Remember, the number line is important here for you to get 4 marks. Illustrated here. 20, the lowest value, and the highest value is what? 92. Then we have the lower quarter, which is 29, the median, which is 56, and the upper quarter, which is what? 70. Are we together on how to come up with a box-Whisker plot?
I have one question. Please go back to your previous slide. So it's 61.5 minus 29 or 29 minus 61.5.
It's 29 minus 61.5. So it's Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. I'm just trying to simplify this because most of you forget this. So I just tell you, after you find the interquartile range, just multiply it times 1.5. This figure, to this end, you add. To this end, you subtract. So 29 minus that, 70 plus that. Are we together?
Yes,
we are.
because I've seen in certain instances where it's done by versa, it becomes 61.5 minus 29.
No, you get a positive.
So
You affect, it's simply this figure. If this is confusing you, then use this rule, the actual rule. You do Q1 minus 1.5 IQR. So our Q1 was what? Was 29 minus 1.5 times the interquartile range was what? 41. So 41. You get the answer of the lower limit, which is negative 32.5, to avoid that confusion. Then you go to the upper limit, Q3 plus 1.5 IQR. 1.5 IQR, the 1.5 is standard. So you go to Q3 was what? 70. Put 70 plus 1.5 times the IQR, which is 40. You compute it. It was 41, sorry, you compute it. Then to give you your final answer is what? 131.5. Then you identify the figures that are out of range. Those are called outliers. So using the box-Whisker, you've plotted all this. Now, of the numbers that we have there, sometimes you may find that others are out of this range. Those are called outliers. But sometimes all of them will be inside range. Those are not, meaning there's no outlier. Now, we want to learn how to describe the skewness using the shape. Now, when you have a skewness which is bending to the right, this means that our skewness is what? It means that our mean is actually greater than the median. We're getting a pause. Our mean is actually less than the median, sorry. So it's a negative skewness. So whenever mean is less than the median, our skewness will be in the negative side or to the left. So whenever we have a skewness, this is skewed to the left. Okay. So when we have a skewness to the right, or when you have an asymmetrical distribution, it means it is even. The left side mirrors the right side. This is called an even distribution. When you have a skewness to the right, to the right. Okay. So this is a skewness to the right. So we have the mean, which is greater than the median. Okay. Now, according to this distribution, the skewness here is giving us the opposite depiction. I think this is where most of the students were getting the confusion, not the confusion per se. According to this book is how Dr. Sabao, I think, explained it. This, according to your, is it's a right skewed, because this is what is being considered as what? The skewness. So in a right skewed distribution, most of the data is concentrated on the what? On the left side. Therefore, the right tail of the distribution is longer than the left, and the mean is greater than the median. So this distribution in this case is right skewed, because this tail here, most of the distribution is bending on the left. I repeat, in a right skewed distribution, most of the data is concentrated on the left side. So this is the right side and this is the left side. So if most of the data is concentrated on the left side, we actually call it a right skewed distribution. So this therefore entails that the right tail is longer than the left tail. So this distribution here is a right skewed distribution. In a right skewed distribution, what actually happens is that our mean is greater than the median. Mean is greater than the median. Now, in this scenario here, this is called a left skewed distribution. A left skewed distribution because the tail, this skewness here, is longer on the left. So when the data is concentrated most on the right, it causes the left tail to be longer. So in this case, our median is greater than, so this median here is greater than the mean. So the mean is therefore less than the median for the Q2. So I think that is where you people were, I think, trying to explain what was explained in class. So now we have a question here of the data which shows the number of days it takes an author to write a chapter in a 15-chapter book. So we're being asked to draw a Box-Whisker plot. So in this case, these are 15. Our n is 15. So how do you find the Box-Whisker plot? First quartile, which is a quarter of n. So a quarter of 15 in this case would be what? Quarter of 15 will be 3.75. So 3.75 to the nearest, it is a fourth number. 1, 2, 3, 4. We're going to pick this part here. The upper quartile is 3/4 of what? 15. It's 11.25. The nearest is the 12th number. So 4, 5, 6, 7, 8, 9, 10, 11, 12. 26 is called our upper quartile. So from what we've discussed so far, can somebody identify the 5 elements that will qualify here quickly? The names are called Maggie, Brenda, Bwanga, Concepta, and Dalisa. The 5 points.
Our median is 13.
The median is what? Half
13.
of n.
Mm.
So half of 15 is what? 7.5. So you pick the 8th number. So she's finding the median, the 8th number. So 4, 5, 6, 7, 8. Correct. Our median is 15. So she's answered the toughest. So Q2 is 15. What else do we have in here? The other 2, other 3. Identify what you are able to see.
Q1 is 13.
Q1 is 13. Next, the other one.
Q3 is 26.
Q3 is what? 26. Correct. What else do we have?
So we have the minimum and the max.
Minimum and the max. What is our minimum?
Which is 9.
9 and what? 49.
49.
Okay. The next could speak out what we need. Kangwa, Miriam, Mwansa, and Nosiku. What is our interquartile range? What is our correction term? And how do we find the outliers? Quickly.
Interquartile range is Q3 minus Q1.
The difference between these two, which is what?
So 13.
13 correction term. Multiply by
That's 19.5.
19.5. What do we do to the 19.5?
Add
We
it
add
to
it to the
26
Add it to the 20.
and subtract 13.
subtract it from the 13.
We get what? You get negative 6.5 and 45.5. So negative 6.5 and 45.5. So which ones are our outliers? I'm here. Which ones are outliers?
49.
9 is out of. All right, so this is the illustration there. Able to tell. Then 49 is somewhere there, which is out of range. So our lower limit of 9 and 36. Okay, so what can we tell about the shape of the distribution? So whenever Q2 is more than the median, what does it mean? So in the problem above here, the median is what? 15. Now, when you calculate the mean of the data, don't include the 49 because it's an outlier. So you need to compare. If Q2 is greater than the mean, and if Q2 is less than the mean, what happens? That will help you identify the distribution. Okay. So in this instance, when you calculate, you need to exclude the outliers. So the outlier is not qualifying to be part of the mean values. So when you calculate all these, excluding the 49, our mean will be 20. Now, 20, if the mean is greater than the median, it is skewed to the right. So according to my definition, whenever there's a bigger value, gap here, it is skewed to the right. Remember what I gave you in my initial note? It still stands to say, if you have these scenarios here, this is a normal distribution. This is skewed to the left. This is skewed to the right. Where there's a bigger gap. But still, you're able to tell by calculating whenever the mean is greater than the median, it is skewed to the right. Whenever the mean is less than the median, it is skewed to the left. That is how it goes. So in this case, I repeat, you can tell that the gap is bigger on the right. So you can say it is skewed to the what? To the right. It's right skewed. However, you can calculate what? The mean by adding everything and dividing by 14. Why? Because one of the 15 figures was what? Was an outlier. So we get 20. And our Q2 was what? 15. So if the mean is greater than the median, we say it's skewed to the right. I hope that is clear. Maggie, is it clear now?
Yes, it is. Thank you.
All right, thanks. Okay, the same can apply here when you're given data. These are 15 figures. So the fourth one and the 12th one, these ones are going to be a Q1 and Q2. All right. Then you come up with a box-Whisker plot. All right. From here, you're able to tell which one is the distribution skewed to the left or is skewed to the right. There's a bigger gap there. I can say it's skewed to the right. But you could still as well calculate your mean. If the mean is more than the median, you say skewed to the right. You can do that. That is the safest way. But however, this I can tell from my 255. Right, I can tell from looking myself. So the mean is 255.2, and here a median is what? 255. So already it's almost normally distributed, but it is skewed to the right. You can see there it's likely to be symmetrical. It's almost close. So it's almost asymmetrical because they are close. These two are approximately equal. So you can comment to say it's skewed to the right, or it can say it's likely to be symmetrical because the mean and the median, whenever they're the same, it is meant to be asymmetrical. It's meant to be asymmetrical. So now we go to the stem and leaf diagram. Question: what is the stem and leaf diagram? This is a diagram which displays the distribution of data by separating the values into a stem and leaf. So the first digit or digits of the number are called the stem, and the last is called the leaf. So if we have 12, 13, 20, so we're going to have 1, 2. So writing 2, 12 and 13, this is 13, 20, we put 2 and 0. So we just pick the last number to be a leaf. This is called the stem. Suppose we had 123, 334, 205. These ones are what? The stems. So we're going to put 12 and 3, that's 123, 13 and 4, 134, 20 and 5. So the last number is what qualifies to be the leaf, in short. Even if we had 1001, 100 will be the stem and the 1 will be the leaf. So you'll be given information like this, for instance. Put it in a stem and leaf diagram. So we have 20s, 30s, 40s, and 50s. and 40s. So these are numbers of 20s, 30s, and 40s. So 28, 34, 42, 47, and 49. So the last row, the leaves are just the last number in short. So if you're given a data set like this one here, 11, 12, up until 56. So we have 10s, 20s, 30s, 40s, and 50s. So here 11 is 1, 1, 12 is 1, 2, 14 is 1, 4, 17 is 1, 7. Then we go now, the 20s. 20 is 2, 0. All right, another 20 is 2, 0. And we have 22, 2, 2. And it goes on until we go to 50 and 56. Now from this data, you're also able to identify. It's a summary. It's a very good summary. Which one is our mode? The most appearing numbers. So we can see here there is a 5, 5, 6, 6, 2, 2, 5, 5, 9, 9. So 25, 26, 32, 35, 39, and 41. These ones are for our mode. The mistake people make is to look for the numbers appearing the most here. Yeah, 0, 0, 0. No, don't take them individually. Look at the ones that are, if we're 555 there, 25 would have been our mode because it's appearing the most there. So mode is the highest frequency. Mode is the highest frequency. So in that case, this is a stem and leaf diagram that we are talking about. So now what happens in the instance where the digits are not there? All right. So if we have numbers like these ones, 8, 9, 20, 25, 143. Okay. So in this case here, we have 08, 09, 09, but 10s we don't have. So you put the number even though we don't have any data sets. This is what I explained in the assignment. People were writing 0, then they jump, they go to 20s, 30s, 40s. They only, you put in the 1 even if there's nothing appearing there. All right. So we also follow in this data set here, we have numbers, we have 160s, 170s. So meaning there, the 220s, there was nothing. We put it there even if there was nothing there. 220, 231 is there. 240 something, there's nothing there. So it needs to come out like that. So you need to find it, make it look like the figures that are not there or have placeholders. Okay. So this is how we do the stem and leaf diagram. Sometimes we may be using stem and leaf diagram for decimals. How do you consider decimals? Decimals as well. Firstly, what you do for you construct the stem and leaf diagram is to round off the figures. 117.2 becomes 117, leave it as it is. This is 104, we leave it here. But if you have 89.9, it becomes 90, you round up. So we don't deal with decimals, all right? But this is 95.7 is 96. So round them up, then you can now do the stem and leaf diagram. So this is 117. Okay. Start from the smallest, maybe 70, 70, 70, 70, 71, 71. And you do the stem and leaf diagram as it is. Am I speaking sense? Are we following through?
Yes,
Yes,
we are.
Yes,
Yeah.
we are.
There are certain things that you thought you knew, but you did not know. It's very important that you have an in-depth understanding of such things. All right.
Sorry, before we move, I've got a question.
Uh-huh.
Like, for instance, this data set that's on the screen started from the 70s. Do we still have to start 0, 1, 2, 3, 4 to 7 and then start constructing our leaves?
Good one. You
We
tap
just start from the smallest
from
digit.
the smallest and the biggest. So if we are looking at numbers
Okay.
from 60 to 90 that are available, there's no need for starting from 0. That's a very good question. You capture what is in between. If we have something at 10 to 90, if they're not 20s, you put them there. Anything that is in between, you capture it. But below it, it's not necessary. I like your question. Is it
All
necessary?
right, thanks.
6, 5, 4, no, that is not necessary. Unless we had a 20 somewhere there. The 20 would have qualified the numbers in between. Did you hear her question, right?
Yes, yes,
Yeah.
yes.
And I've answered it correctly, yeah? Okay. So this is how the stem and leaf diagram goes. I don't want to overemphasize. I just want you to understand that the concept goes as far as I've explained. So I now go to calculating our mean, our variance and standard deviation for a population. So sample, our mean is called X bar. Whereas population, the mean is called mu. Sample, the variance is called S squared. Whereas population is called sigma. Sample, standard deviation is simply an S. In a population, it is simply sigma. The formulas only differ when it comes to this guy here. All right, when you're dealing with mean for a population, summation of X over N. For a sample, same formula, summation of X over N. All right, for variance, summation of X over N. Everything over N. For a sample, summation of X squared over N. Everything divided by N minus 1. You've seen the difference, which is down there. Standard deviation, you just square root the variance. Same, anywhere you go, standard deviation is simply a square root of the variance. And the formulas are way together, except that variance has two formulas. It's a prostitute a figure, because depending sometimes on the data that you're given, the variance is simply the X minus mu over N. So variance can be also written by summation of what? X minus mu over what? N. Then you square these figures there. This is also called the variance, depending on which one is okay with you. All right, so now we're going to look at the data set below. So we're being given a decade and the number of hurricanes that were reported in the US between 1901 and 1910, we had 18, until we go to 1991 to 2000 at 14. So we're being asked to calculate the variance and the standard deviation. So we can use this formula here to find the variance. First, we find the mean by adding up all these figures from 18 to 14 divided by the sample size, which is 10. So we get to 16.7. So we subtract from each one here 16.7, and the answer is square it. Okay, so we subtract from each of these values. 18 minus 16.5, then we square this answer. 21 minus 16.5, then we square it. Everything we're subtracting and we square them. The total is simply what we call the variance. So once we get that figure as a variance, we now, and the total is not the variance, it's sum of X minus mu squared. Then we divide by the number of what? Entries. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we divide by 10. So this is what we call our variance. Our variance is 13.21. I personally do not like this formula. But anyway, it is what it is. And when we go to using this other formula that I like, you don't subtract 1 if it's a population. Question is, how do I know it's a population? It's a sample. You'll be told in the question, you need to tell. The information that is given shows the number of hurricanes. It's not a sample out of it. So sometimes people get wrong because they do not understand what whether it's population or it is a what? A sample. If we go in a shop, we say a shop randomly selected 7 people who came to buy. So already that is a what? A sample. So you need to be able to distinguish. MBA students at UNILAS taking QM. Out of them, 70 were found to also take MTP. So that's a sample. So you need to really understand what to and what formula to use. So it is up to your experience in the questions that in the scenario. So when we go to this, are we together so far? Was that clear? Have I lost anyone? Have I lost anyone? Are we
We're
together?
here.
All right, great. So sometimes you can use these figures here. 18, you square it. Figures, you square them, you get the summation of x squared. Okay, then divide by n, everything over n. You still get the same figure. All right. So this is a formula that I like. It's easy. I said if you have numbers like 2, 4, 6, these are values of x. You square them. 2 squared is what? 4. 4 squared is 16. 6 squared is 36. You total up. This is called summation of x, which is 12. This is called summation of x squared, which is what? 56. And our n is 3. How do you find the mean? It is summation of x over n. So 12 over 3 is equal to what? 4. But for the variance, summation of x squared and a summation of x to the power 2 over n over n. This is now called population variance. Dividing by n. If you subtract 1, it becomes what? Sample variance. So that's what I'm trying to differentiate. So be very careful on which of the 2 formulas to use, because sometimes the examiner wants to know whether you're going to give the disparity between the 2. The standard deviation is what you square root our variance. So we also have an important feature which is called the coefficient of skewness, or CV. Coefficient of skewness usually measures the percentage of variation in the data relative to the mean. This is important to show which one is more variable. You multiply by 100 if you want to leave it as a percentage. So for instance, our standard deviation is 3.63, and our mean in the instance that we just calculated is 16.7. So what we get here is 21.7. So the data is volatile by 21.7%. We are given data here. This shows the number of students enrolled in all the 5 colleges. So O simply tells you that this is what a population. So calculate the variance and the standard deviation, and somebody quickly makes an error by doing n-1. Please understand that the population and the sample are different. Total them up, we get the mean. Subtract from each of these ones here. So 18 minus 22.1 squared, 22 minus 21 squared, and then the total here, which divide by n, 1, 2, 3, 4, 5. So we divide this by 5. What we get is called our variance. The shortcut I love is just square this there, 22 squared there, 25 squared there, 26 squared there, 15 squared there. This is called our summation of x squared. This is summation of x. And just use the formula summation of x minus summation of x all squared over n divided by n. So 2334 minus 106 squared over 5 divided by 5. So the answer you get is 17.36, which is the same answer. When you square root that, we get our standard deviation. So this is how we calculate these. All right, so the standard deviation is when you square root this data set to get our population standard deviation. So to get our coefficient of variation, we simply divide our standard deviation over mean times 100, which is 19.7. So this is how it goes. So we may go on and on, but the concept is simply the same. Understand and differentiate which one is a mean and which one is a what? Is a population and which one is a sample. So here we are told that the following data shows the number of students absent from a school each day. So we have this. We have to calculate our variance and standard deviation. Be careful. The variance for a sample is slightly different from that of our population. But in this case, this is going to be considered a sample because only 5 schools from the entire school is included. Only 5 school days from the entire school year are included. So we're told that the data set here shows number of what? Students absent from a school each day a week. So there are how many weeks? There are 52 weeks in a year. They have just looked at week 1, week 2, week 3, week 4, week 5. So this cannot be a population, but a sample. So we're going to use X bar, not mu. That is an idea. Then to calculate the standard deviation, we're going to use n-1 at the denominator because this is now a sample variance. So that's what I needed to just illustrate. Similarly, if you're using this formula, we're going to subtract n-1. The figures we're going to get are the same. It's tricky and fearful sometimes, but most of the questions you ask or he has asked so far mainly pertain to what? To a sample rather than a population. But I've just explained for you guys to know the distinction between the two. Are we together? So I'm hopeful you're learning quite a lot just from this, the mean, the variance, and standard deviation. There are things that you thought you knew that I think you did not know. So calculating the coefficient of variation is a percentage. You just have, sometimes you can leave it as a figure as it is, or as a percentage. So all these are simply pointing the same principle that I've just explained. You need to understand. Sometimes they'll ask you to calculate and compare between two. So here we're given to refer to the number of runs hit by players Jefta and Roderick. So these are the runs here. So we're being asked to calculate the standard deviations for each player. 8 consecutive baseball seasons. Looking at the runs. So we calculate we're calculating the sample variance and standard deviation for each of them. All right, and we also calculate the means for each of them. Then now, a key question is how to explain the coefficient of variation for each of them. So standard deviation over mean times 100, here we get 30.6%, here we get 19.8. So Rodrigues runs, okay, this is for Jefta and Rodrigue. So Rodrigues runs here are showing a 19.8% coefficient of variation, which is lower than that of what Jeta's record, which is 30.6. So here, what is the implication? Okay. So the variation, the inaccuracy of Jeta's is higher than, so this one, the higher the figure, the more volatile the results are. So we use coefficient of variation to compare the standard deviations because it gives us the differences that are there with regards to the mean. The higher the CV, the more volatile it is. So I will end here for tonight. We'll end here for tonight, unless there are any questions from what we have discussed.